This problem says find an equation of the tangent line to the graph of 2x cubed minus x squared y plus y cubed minus 1 equals 0 at the point P, which is 2 comma minus 3. So what we don't have here is an explicit function of y equals some function of x. We don't have that, but we have a equation that says that this on the left is equal to 0. Now that we have a point here, if this point were some x1 comma y1, and if we wanted an equation of the tangent line, we could say that using the point slope form, y minus y1 equals m times x minus x1, where this is the slope of the tangent line. We have the point here that is on the graph. It would be nice to have that slope. What would the slope be if we had a explicit function y equals f of x? Then the slope would be the derivative at that value of x, right? But it's going to be hard to get a y equals all by itself, let alone take the derivative of it. So what we can try to do is, we've got this equation here. Now if we take the derivative with respect to x on the left side, it'll be equal to the derivative with respect to x on the y side. So how would you do this? Take a look at this. This is obviously 0. But how do we handle something like this with x's and y's? Let's number these. Let's call this 1. Let's call this 2, 3, and this 4. Okay. And then at the end, since it's just sums or differences of these terms, we'll put them all together. Let's work on 1 first of all. It's not too bad. What's the derivative with respect to x of 2x cubed? Well, this is nice. It doesn't have any y's in it. This would be, by the power rule, just 6x squared. So let's put right here. Now we're going to work on number 2. How do we take the derivative of x squared y? Think about this. If you remember the chain rule, you know that we have to consider, or if you were the product rule, we have to do the derivative of x squared. The derivative of x squared is 2x. Now we've done the derivative of this, and we'll do it times this. And now we have to leave x squared alone. Now this, what's the derivative of y? What would this be? we can just write y prime. Let's leave it at that. Let's not try to figure out what y is in terms of x. Let's just say that the derivative of y is y prime. We'll just implicitly assume that it's y prime. So let's write all of this for 2. So this would be 2xy plus x squared y prime. Remember, this y is a function that we don't know exactly what it is, but it's just the function. And this is the derivative of the function. So y and y prime are two different functions. How about this? What's the derivative with respect to x of y cubed? Now this is like a chain rule. What is the derivative of y cubed? Well, we've got the power rule. We're doing 3y squared, but then we have to do the y prime. It's like y is our other variable. It's like doing a u substitution. So this 3 is 3y squared y prime. And for the derivative of -1, it's a constant, is just 0. Now let's put these together. So this derivative is equal to 1 is 6x squared minus this. So imagine this would be minus 2xy minus x squared y prime. This is plus 3y squared y prime. I'm not going to write plus 0. Now we're saying that all of this side is equal to this side, which is equal to 0. Here's where the technique of implicit differentiation involves getting this y prime by itself. Let us look at the terms here that have a y prime on it. Okay, we can write y prime times, let's as if we're factoring this out. Let's do this one first since it's positive. If we factor a y prime out of 3y squared y prime, we have 3y squared. Now, the only other term that has a y prime is this. So we do minus x squared. So y prime times these. And we're going to move these two, which don't involve a y prime, to the other side. Since this is negative, let's add 2xy to both sides. And this is a positive 6x squared, so let's subtract 6x squared from both sides. Okay, now we have y prime times the quantity 3y squared minus x squared equals 2xy minus x squared. Can you see what we would want to divide both sides by if we want to get an equation for y prime? 3y squared minus x squared is equal to y primed. And this would be the slope. This is perfect because we have an x and a y at one point. We want to know the slope at that point so that we can figure out an equation of the tangent line at that point. So let's plug in 2, -3 into this function. What do we have in the numerator? 2 times 2 times -3. 4 times -3 is -12 minus 6 times 2 squared is 4. 6 times 4 is 24. -12 minus 24 is -36. So I'm going to write slope so far -36. Okay. What do we have here? 3 times -3 squared is 9. So 3 times 9 is 27 minus x is 2. So 2 squared is 4. 27 minus 24 is 23 last time I checked. So now we know the slope of the tangent line at that point. And we know that the x point is 2 and the y point is -3. And you remember the point slope form? Y minus the y value, -3. So y plus 3 is equal to the slope, -36 23rds, times x minus the x value is 2. So the equation of the tangent line was y plus 3 equals -36 23rd times x minus 2. The important part was differentiating both sides here, remembering the chain rule and how to get through factoring the y primes all by themselves so that you have an equation of y prime in terms of both x and y's, and using the fact that you know a point and solving for the slope of the derivative. The thing is, you never know exactly what the function looks like as y. You never know what the function y looks like all in terms of just x's. That's why it's called implicit differentiation, because you've got x's and y's. So that was the technique used to solve that problem. This problem says show that y squared equals x determines an infinite number of implicit functions. So let's use the technique of taking the derivative of both sides with respect to x. So we have y squared equals x. What happens if you differentiate both sides with respect to x? So we've got dx of y squared equals dx of x. Okay, so using the chain rule, this would be 2y times y prime equals the derivative of x with respect to x is 1. So that means that y prime is 1 over 2y. What have we got by now? We still don't have y equals some function of x But do you recognize, perhaps you recognize from this, does this look similar to, this is just a jump. Is this similar to y equals the square root of x? What's the derivative of x to the 1/2? This would be 1/2 x to the negative 1/2, which would be 1 over 2x to the 1/2. You see how if y is equal to x to the 1/2, this is 1 over 2y. That proves that there's one equation, but this says determine if there's an infinite number. To figure out that, let's look at this. The square root of x function looks a lot like this. Keeping this same shape function, what would this one be if this were some value a? It would be x minus a to the 1/2. What's the derivative? If this were y, then y prime would be what? Would this be 1/2 x minus a to the negative 1/2? What's the derivative of x minus a? It would be just 1, right? So this would also be 1 over 2y. And this, as we can tell, there's an infinite number of these. So if this relationship is held when y equals x minus a to the 1/2, and there's an infinite number of possible a's, infinite possible a values, and for each one of them the derivative is 1 over 2y, then you've shown that there's an infinite number of implicit functions where y squared equals x. This problem says find an implicit function f of x and state the domain of f. So as we saw in this previous problem, for an equation there's possibly an infinite number of functions y equals f of x. So we have to use creativity and figure out what's one possible function where this is always true. The absolute value of x minus y equals 2. So let's think for a while. Let's draw some pictures of possible functions that would satisfy this, at least over a certain domain. And if we find one, we have to state the domain. If we don't have a specific technique, we could think of a coordinate point that solves this. Well, let's say, what if, let's draw some points where this is true. If x were equal to 0, what would y have to equal? Well, it could be either 2 or negative 2. Let's say that it was 2. You know, because 0, 2 is on this line. What if x were equal to 1? 1 minus what absolute value is 2? Well, if 1 minus 3 is negative 2, absolute value is 2, so 1, 3. 2 minus what? Well, 2 minus 4. This function is a line. What about for negative values? What is the equation of this line? 0, 1, 2, 2, 3, 4. It appears to have slope of 1 and y-intercept of 2. So you could say y equals x plus 2. Is this valid for over the domain? Is this satisfied when x is, say, negative 1? Negative 1 plus 2 equals 1. This is the x and this is the y. Now, is the absolute value of negative 1 minus the y value is 1 equal to 2? Negative 1 minus 1 is negative 2. The absolute value of negative 2 is 2. So it appears that this is on the line. What about x equals negative 2? Okay. Negative 2 plus 2 equals y, which is equal to 0. So this is x and this is y. How about negative 2 minus 0, absolute value, is negative 2. The absolute value is 2. Is it appearing that this is always true? Let's say that x equals some value a, where a could be any value on the real number line. Let's say x equals a, negative or positive, or even 0. Then y would equal a plus 2. Okay. Now, if x is equal to a, and we're subtracting y, which is a plus 2, a minus a plus 2 is 2. The absolute value of 2 is 2. So this function y equals x plus 2 appears to be one function where this is true. The domain of y appears to be negative infinity to infinity. That's just one possible implicit function where this is true.